So we're going to introduce the logarithm in this section, and I'm going to do it the following way. I want us to take a look at f of x is x cubed and g of x is 3 to the x. Which one of these is the exponential function? G of x, good. So you've got a fixed base to a variable power. Now in both cases we can find the inverse of these functions. So the first step in finding the inverse is to replace the function by y. So y equals x cubed or y equals 3 to the x. Second step is to interchange x and y. And so far things are looking pretty good. What happens next? What do we do next? Solve for y. Good, so in this case over here I get the cube root of x equals y, or better yet, f inverse of x equals the cube root of x. So there we go. We've got the inverse of f. But you're running into a problem here. With what we have up to date, there's no way to get y by itself. You can't take like the y-th root of both sides and get y by itself. It's just not going to work. So what we do is we introduce a new function, and it's the logarithm. So we get the log base 3 of x equals y, and that's our inverse function. G negative 1 of x is the log base 3 of x. So the logarithm is just the inverse of your exponential function. Now, in more general terms, we have it on our handout. And this should say 4.3, not 11.4. Sorry, I plagiarized myself. I owe myself some royalties. But the general statement that you should know and be comfortable with is this one up here. Now here's a little test-taking tip for yourself. A lot of times when you take a test, there's certain little facts, formulas, things, figures, dates that you need to remember. When you get your test, write them down right away. It's called a memory dump. So before you forget things, before you forget the exact relationship of this, or you forget what year the Magna Carta was signed or something like that, then write it down. And then later, when you're in a panic because you're running out of time, you don't blank on it, you've already got it written down. So what is the logarithm saying? The logarithm is saying, really, it's asking you, well, what power of a gives me this? So a to the y power gives me x. A to the y equals x. That's why these two are equivalent, and we can use one as the inverse of the other. So in fact, kind of a cool thing that you can do with Desmos that you can't necessarily do with your graphing calculator is kind of flip things around. So let's go back to our home screen, ditch this. Let's graph a couple exponential function, or an exponential function, y equals 2 to the x, like that. Now, do you remember what the graph of an inverse function looks like? How do I find that if I know what the function looks like? It's flipped around the line y equals x. So here's the line y equals x. And this is what I was telling you that you can't do in your calculator. You can just interchange x and y. X equals 2 to the y. And you can see that this function is a mirror image of this one. So whereas the one function you have a point at 0, 1, the other one you have a point at 1 and 0. One function grows quickly, the other one grows slowly. But they're mirror images of each other around that line y equals x. All right, so let's try and understand these things a little bit more. We want to make Tyler comfortable before we go home here today. So let's do that. So that's down here, understanding these exponential functions. So the first example is kind of already done. Log base 2 of 16 is 4. All right, well, why is that? Well, that's true because 2 raised to the 4th power gives me 16. That's what the logarithm is. It's telling you what exponent you would use for the base of 2 to give you 16. 2 to the 4th power equals 16. And that's right here. Let's try another one. And for a while, these are going to be some easy numbers that we can do kind of almost in our head. Let's take a look at the next one. Now, when you're doing these things, you should be asking yourself this question. What power of the base gives me this? So 4 to what power gives me 16? 2. And then equivalently, that'd be 4 to the 2 power is 16. Let's do some more. Move down from there. What power of 5 gives me 125? 3. Ooh, look out. I think you're understanding this. Good job. So 5 cubed is 125. So this is your statement using logarithms. Here's your equivalent statement using exponents. So why don't you try maybe the next 3 here? See if you can come up with those. And, again, keep asking yourself, what power of the base gives me this number? And then try and rewrite it using exponents. All right, so let's see. Keegan for the first one, Katie for the next one, and then Paige for the one after that. So go ahead, Keegan. Want to give this one a shot?
Yeah, 2.
And then how would I rewrite that?
9 to the 2nd power equals 81.
Perfect. All right, Katie.
4 84 over 4 equals 64.
4 to the 3rd power. All right, so if I rewrite that then, it always works like this. It's always going to be the base to this power equals this. So rewriting it using an exponent would be 4 to the 3rd power equals 64. Paige, were you able to get the last one? Perfect. And this should always check. You should always be able to check this on your calculator directly. And if you guys are good, maybe I'll even show you how to do this directly on your calculators as well. Now, let's do some that are going to start requiring us to think a little bit. Starting with this one, log base 7 of 7. Cooper. What? Yeah, 1. That makes sense. 7 to the 1st power is 7. Cool. Victoria, how about log base 8 of 1/8? Well done. -1. 8 to the -1 is 1/8. Remember, when you have a negative exponent, you can take the reciprocal. So this is really 1 over 8 to the 1st power, or just 1 over 8. Nice. Now, Victoria did a good job on that one, and maybe it gives you a clue for the next one. What would log base 6 of 1/36 be? -2. Perfect. So -2. Yeah. So 6 to the -2 power is 1 over 36. And you can see that if you realize that this is 1 over 6 squared, and of course 1 over 6 squared is 1 over 36. Good job. Good job. Some more kind of think problems here. Log base 7 of 7 square, well, square root of 7. Good job, Matt. Thank you. So that's 1/2. And you might remember this as soon as we put it in exponential form. What would it look like in exponential form? What to what power equals what? Thank you. 7 to the 1/2 equals a square root of 7. Remember, something to the 1/2 power is just like taking a square root. So those two things are interchangeable. We're seeing a similar example to what we saw before. log base 10 of 10? Anyone? 1. All right. 10 to the first power equals 10. Now that's suggestive. We've seen it a couple times. So let me write down kind of below here some of the properties that you can kind of look out for. And properties. We'll start with this one. Log base b of b is 1. Anytime the base and the argument match, the argument is what you're taking the log of. Anytime they match, then log base b of b is 1. So there's going to be more properties of logs that we're going to deal with. Let's see if we can figure out a couple more of these. What about log base 10 of 100? 2. 10 squared is 100. Now some of these you might kind of get bored, but we can do these in our head almost, right? I mean, how many zeros are there here? 3, so that's 10 cubed. 10 to the 4th. Negative 2, good. Now at this point, let's take out our calculators and play around with those a little bit. Let's learn some things from our calculators. So log base 10 is kind of like a default. Log base 10 is what's called the common logarithm. So let me put that up here. Log base 10 of x is just log of x. It's kind of like square roots. We don't typically write the 2 out in front of a square root. It's just understood that that's a square root. It's a 2 out in front. Same thing with logs. Now with log base e of x, which you'll hardly ever see written, except by me, log base e is a natural log. It's abbreviated as ln of x. So it's just some notation that you need to be comfortable with and familiar with. Okay, so let's finish this up then. This is negative 2. How about this last one? You can do that on your calculator. Log 0.001. Yes, exactly, negative 3. Carol, you want to give that one a shot? What would this look like if I rewrote it using exponents? What to what power equals what? If I rewrote it using exponents, what would it look like? So, like this one, it would be 10 to the second power equals 100. How would it look here? 10 to the negative third equals 0.001. So that's rewriting it using exponents. Now, we can go the other direction as well. We can start out with some that are written in exponents and write them with logs. But let's hold off on that for just a little bit and do some of the problems that are in the book. Some of them we've kind of effectively already done. Let's see about some other ones, like problem number 12. Log base 5 of 1 over 125. So we got to think about, well, gee, what power of 5 would be 125? One thing that you might notice is 125 is 5 cubed, right? So what power of 5 is going to be 1 over 5 cubed? Tyler, you negative 3. Good. Now your answers to these problems should check. They should make sense. So you should be able to kind of unwind them using exponents. Is an equivalent statement using exponents? Anmar, what would this be? To rewrite this using exponents. good. 5 to the negative third equals 1 over 125. And you can check that on your calculator. You can check that 5 to the negative third gives you the same decimal value as this. Or you can just convert it to a fraction. 5 raised negative 3, 0.008. Hit the math key, answer the fraction. Boom, 1/125th. So check these, please. Make us both happy if you get them right. Let's try part B. Log base 8 of 4. You know what? I'm going to give this one to you because we're going to discuss it later. Is 2/3. So for one last time, let's rewrite this using exponents. I'll give you a chance to write that ahead of me. Ready, set, go. So John, equivalently using exponents, what would this be? Perfect. And again, you can check those things on your calculator. Well, once you get comfortable with this, and thanks, John. Once you get comfortable with this, you can start solving exponential equations or logarithmic equations. We're going to start with logarithmic equations in the form of problem number 14. So we've got log base 6 of z equals 1. Probably a couple ways you could do this, but the fastest way to do this is to rewrite it using exponents. So let's see about doing that. Jeff, what would this look like if I rewrote it using exponents? 6 to the first equals z. So z equals 6. That makes sense. If you think about our properties of exponents, or excuse me, our properties of logs, if these things are equal, then you're going to get 1 for the logarithm. Since I got 1 for the logarithm, that means those things are equal. So that's making sense out of it a different way. But as far as calculating it is concerned, I think the fastest and most direct way is just by rewriting it using exponents. Alright, so let's practice a couple that go the opposite direction. We're going to start out with exponents and come up with logarithms. That's a little bit more challenging. So let me let's remind ourselves, this is your exponential statement, that's your statement using logarithms. So overall what you have here is of the form a to the y equals x. And we're going to rewrite it using logs, so it'd be log base a of x equals y. And let's see how we do there. Well, really, one way to do it is just to kind of line things up. The base is a, so okay, that'd be the log a is 10, log base 10 of x. What's x in the first example here? 1,000 equals the exponent, which is 3. Log base 10 of 1,000 is 3. Okay, perfect. That makes sense. Let's move down to the next one. And again, line things up. What base of the log are we dealing with? 3. Now just a quick comment about the base. The base is written as kind of like a subscript. It's below the level of line, maybe a smaller font than everything else. So kind of be careful of that. If you write it on the same line, and it starts to get a little bit confusing. Log base 3 of what? 1 over 81 equals -4. All right, there's several more there. Why don't you give them a shot? I'll walk around, see how you're doing. Make a mathematician out of you. All right. Okay, so let's run through these. Log base m of p equals n. Log base b of 2/3, again, equals the exponent, equals r. And a couple bonus problems. Log base 27. So that's always going to be the base of this number of 1/9 equals -2/3. And finally, log 0.001 of 10 equals -1/3. Okay. How are we looking on converting exponents to logarithms? You okay going back and forth on that? All right. That is, going back and forth is something I absolutely expect, and I hope I've given you a lot of practice so that you're comfortable with that. Let's continue working back and forth between these things, and in moving back and forth, we're going to be able to solve exponential and logarithmic equations. We'll start with logarithmic equations. Problem number 36a. So log base 3 of x equals -2. Let me just take a peek at the instructions, what they want us to do here, but probably just solve. It says, use the definition of logarithms to find x. Well, again, like I say, probably the easiest thing to do is to rewrite this using exponents. Close. So Lucas, let's start by rewriting it using exponents. What would that be using exponents? All right, good. 3 to the -2 equals x, and then that's 1 over 3 squared, or better yet, 1 over 9. All right, maybe that's what you said. I'm not sure. Yeah, okay, yeah. So 1/9. Yep. Let's try another one. And let's move to problem number 38. 38's a good one. We'll slow things down a little bit because we're going to start working with the natural log. So let's see what we got going there. ln of x equals -1. ln of x equals -1. Now, a little while ago I said that probably the only place you're going to see something written is right here by me. What base is understood to be with the ln? So it's log base e of x equals -1. I think it's a good way to start out these problems, writing it like that, because it gives you a base. It gives you something to grab onto as you're trying to convert this. So let's rewrite this using exponents. Michael, what would that look like using exponents, please? Yeah, e to the -1 equals x. And that's something you can calculate. You can get that off your calculator. The reciprocal of e. Yep. Yeah. Now, thing is, you never want to actually type in e into your calculator. Make it do it with all the built-in functions. So, as a reminder, there's a couple places you can find e. If you just want e itself, it's right here above the division key. So you can do 1 divided by, and then hit the second function, and then the division key, that's 1 over e. Or you could just do e to the -1st using the ln key off your calculator. So second ln -1. You should still get the same thing, about 0.3678, etc. All right. One of your fellow students who couldn't be with us this morning sent me in something about the probability of, certain events not happening. Always turns out to be something close to 1 over e, or 1 over 1 minus e. No, 1 minus 1 over e. There you go. 1 minus 1 over e. So about 63% for a large cross-section of pretty seemingly random events. But we're not going to go into that here. Let's take a look at part B. Ln of 1 over e equals x. Now there's a couple ways you can calculate this. Let's see if we can't think our way through it, and then we'll also try calculating it directly. Because really all you have to do is calculate this. I mean, we've already got x by itself. But let's start by understanding what log or ln is. It's log base e of 1 over e. Or better yet, let me rewrite that as log base e of e to the -1st power. Other way. So as you're looking at this, you're asking yourself, what power of e gives me this? What power of e gives me 1 over e? What should x equal? -1. And I like this demonstration down here. It kind of hints at something else, which is another property of our logs. And that is, these two things look like they're canceling. And in fact, they are. The reason they are is because the logarithm and the exponential of the same base are inverses of each other. And they're going to cancel out exactly. So let's go back and add that to our little properties list. So here's our properties list. Let's add log base b of b to the x equals x. So if you have an exponential function and the log of the same base, those taken one then the other cancel each other out because they're inverse operations. It's like adding 6 and then subtracting 6. You're going to get back to where you started from. What if I did it the other way? What if I did log, or just give me b to the log base b of x? What do you think is going to happen there? Well, think of it this way. This term right here in the exponent, log base b of x, that's the number that you raise b to get x. So if this were like a 10 and a 100, log base 10 of 100 would be 2. And then you raise that 10 to the 2 power. So they're going to cancel each other out. Let me see if I can't give you a good number example that we can work through kind of slowly. Let's do 5 to the log base 5 of 125. And let's figure that out slowly. So let's start out with 5, log base 5 of 125. We've already done that one today, I think. What power of 5 gives you 125? 3. All right. And now when I raise 5 to the 3rd power, what do I get? 125. So you're kind of going in a circle, right? You figure out, well, gee, what power of 5 gives me 125? Okay, it's 3, and then I raise 5 to that power. So then you get back to 125. They cancel each other out. They're inverse operations. All right, so that's another one of our properties. I suppose there's one other property here that I could add. Log base b of 1. What power of a base gives me 1? 0. All right, so those are some good properties that'll help you work your way through this section. Let's go back to this one. Some of you might not be entirely comfortable with this. You might look at that and go, you know, I just can't wrap my head around it. And that's okay, because technology is going to come to your rescue. So the only thing we have to figure out is how to put this into our calculator. So we're going to hit the ln key of 1 divided by e. You should be able to get -1. The only thing to remember is where you can find the e, and it's right above the division key. Hit the 2nd key for that. Let's do some more here. Problem number 40. Log base 4 of 2 equals x. That's part A. Part B kind of flips things around a little bit. Log base 4 of x equals 2. Let's start with the second of these. Part B. Suggestions. What can I do to help solve part B? Exponential form. Absolutely. So if I put it in exponential form, Katie, what would I get? Good. So I get 4 to the 2nd power is x. Basically, x is 16. Perfect. Should I put this one in exponential form? Not really. I've already got x by itself. I just need to kind of figure out my way through this. What power of 4 gives me a 2? 1/2. Now, if you did take the time to put it in exponential form, 4 to the x equals 2, you want some power of 4 to get 2. Well, the relationship here is that 2 is the square root of 4. So that power that gives you the square root is 1/2. So basically 1/2 for x. Now, if you guys are on top of things, participate lively and actively, maybe I'll show you a really cool trick to do this on your calculator. But for now, let me share with you what's called the change of base formula. And at the very least, I'll give you the change of base formula on an exam. Okay, so the change of base formula, that's for calculating things when you don't have a nice value like a 10 or an E here. Those are the ones that are built into the face of your calculator. You can calculate those directly. But if you have something else, log base b of x, then a way to work around that is to calculate the log base 10 of x divided by the log base 10 of b. Now I'm not going to write the 10 here or here because those bases are understood. Let's check that out for the current example. Log base b, or excuse me, log base 4 of 2 would be the log of 2 divided by the log of 4. It's a log of this divided by the log of the base. Again, when working these formulas, you got to be careful with your division. Log of 2. I keep on wanting to do that. Log of 2 divided by the log of 4. The place that it's easy to make a mistake is to not put a right parenthesis around the 2, because that closes off the log. It says you're only taking the log of 2. If you didn't, if you had it like this, then you're going to take 2 and divide it by the log of 4, and then take the log of that. That's going to be something much different. Let's try a few more here, and then we'll work with the graphs to finish up this section. Let's try problem number 44. So log base x of 6 equals 1/2. Keegan, what would this look like if we rewrote it using exponents? X to the 1/2 equals 6. Now, to finish solving here, what do I need to do? Well, one way to look at it is to raise both sides to the reciprocal power here. I want to get x by itself, so if I raise both sides to the square both sides, then I get x equals 36. What did I say about something to the 1/2 power? What else could that be written as? Square root of x. So another way to think of it is the square root of x equals 36. And again, squaring both sides gets the job done. X equals 36. I think, however, that a nice general way to think of these problems is to raise both sides to the reciprocal power. That's a very efficient method to solve a lot of problems like this. So let's look at part B for problem 44. Log base x of 3 equals 1/3. So log base 3, no, is it log base 3 or log base x? Thank you, log base x. All right. Log base x of 3 equals 1/3. So see if you can't solve on that one. Victoria, what's that look like when I rewrite that using exponents, please? And what should I do to solve? All right. Reciprocal power is 3. If I cube both sides, then I get x is 27. Nice. Thank you. let's finish up by looking at the graph of these things. And to kind of get a handle on the graph of a logarithmic function, we're going to approach things this way. So let's graph log base 2 of x. So that's the function that I want to graph. Now, you might look at that and go, yeah, I don't know, man. What values of x do you want to put in? That's going to be kind of tough. So here's what I would suggest. Instead of graphing this, let's rewrite it as an equivalent expression using exponentials. So Emily, if I was to rewrite this using exponentials, what would it be? 2 to the y equals x. Now here's my suggestion. And thanks, Em. I suggest that we put in values for y and get values for x, because we've got x already by itself, right? So we're just going to twist things around a little bit. We'll put in values for y and get values for x, but that's okay. It still gives us coordinate pairs. And the values that we're going to choose are going to be simple values. We're not going to give ourselves values like pi or square root of 2 or e or something like that. Let's choose simple numbers. In fact, let's start from the bottom up. 2 squared is 4. 2 to the first power is 2. What's 2 to the 0 power? 2 to the negative 1? 1/2, and 1 over 2 squared. For the last one, 1 over 4. So, great. There's your values. Now it's just a matter of graphing these things. So let's give ourselves a little graph. Let's see. If you want to borrow a ruler, I've got some up here. What you're going to see is something that we saw kind of earlier. And that is the opposite or the inverse of an exponential function. So 1, 2. You know what? Let's see if I can't make this a little bit bigger. Sure, why not? Let's make this a little bit bigger to give ourselves a little bit more room. So each one of these tick marks is going to represent a unit of 1/2. So 1, 2, 3, and 4. And I'm doing that just to give myself a little bit more room along the x-axis. Let's take a look at the points that I have to plot. I've got points at 4 and 2. So that's out here, 4 and 2. And then I got another one at 2 and 1. One at 1 and 0. 1/2 and negative 1. And 1/4 and negative 2. So here's my function. It's a very, very slow growing function. In fact, to get all the way up to a height of 4 on the y-axis, just to get up to a height of 4, where would I have to go? I'd have to go out to 16. To get out to a height of 6, I'd have to go out to 64. It's a very, very slow growing function. One point that you should be familiar with for these graphs is they pass through 0, 1, or excuse me, 1, 0. But another thing that I want you to take note of, take a look at the y-axis. The equation for the y-axis is x equals 0. Do you think this graph ever really touches the y-axis? Just a guess. No? All right. Well, tell you what. Let's see if it does in a different way. If it does, then we should be able to take the log of 0. Now, we're not going to deal with the log base 2, but just try taking the log base 10 of 0. Type that into your calculator. What do you get when you try and take the log of 0? It should tell you in no uncertain terms. Domain error. All right, it's outside of the domain. So when I look at this and I ask, well, what's the domain of the log function? Domain is going to be 0 to infinity. The question is, should I use a bracket or parenthesis on the 0? Parenthesis, because it's not defined at 0. How about the range? Yeah, all real numbers. This goes all the way down to negative infinity and eventually all the way out to positive infinity. So negative infinity to infinity. And if you're going to look at this in contrast to the exponential function, y equals, say, 2 to the x, or any exponential function like that, the domain and range are just interchanged. The domain here is all real numbers. And the range here is 0 to infinity. So they just flip-flop. On your handout, we could practice a little bit with graphing these functions. Now, as with our graph of the exponential function, the log function has its own asymptote. That's that line right there, the y-axis, x equals 0. So let's play around with some graphs here. And not that many people would recognize it, but I accidentally drew the wrong graph. This is really the graph of ln of x. So I don't know, maybe I should change some of our examples. Let's just write this as y equals negative ln of x, y equals ln of negative x, 1 minus ln of x, and minus ln of minus x. And that's just in recognition of the fact that I accidentally drew the wrong graph here. This is y is the ln of x. So same shape graph. The important thing to see is that it passes through 1 and 0. But let's see if we can't figure out what some of these other graphs are going to look like based on this graph, just by translating it and shifting it. And we'll start with y equals negative ln of x. Let's see if this one will work better. No, that doesn't work. What's that negative going to do to the graph? Yeah, it's going to flip it. So it's going to be flipped upside down. So still going to have a point through 0, 1. All right. Not my best. All right, but that graph's been flipped around the x-axis. What's this going to do if I put a negative inside the log? How's that going to affect my graph? Yeah, the negative is going to flip it around the y-axis. So take this and reflect it around the y-axis instead of having a point at 1, 0. Thanks. Where's this point going to be in my new graph? Thank you. Yeah, it's going to be flipped around here. So it's going to look like a mirror image around the y-axis. You're going to have a point at -1, 0. So you're going to get this kind of graph. I'd probably rewrite this in order to try and make better sense out of it. And the way I'd rewrite it is, I'll write that as negative ln of x plus 1. And maybe that's a little bit easier to interpret now. Paige, what two things have been done to this graph compared to the graph of ln of x? If it was in parentheses, then it would be a horizontal shift, but that... All right, so there's going to be a shift up by 1. How about the negative out in front? Yeah, that's going to flip it. So basically, you can take this graph and shift it up by 1. So if we start out with this graph, then this point gets shifted up by 1. And now on this axis, that's a 1 right here. So you're going to have a graph through there. And let me just turn this around a little bit to draw it. So y equals negative ln of x plus 1. Nice. All right. A couple more to finish this up. And let's look at this one over here. They're just going to be the same shape. It's just going to be a little bit different. The log function is going to grow even slower than the ln of function, the ln. So it'd be very, very similar. So what I want you to get out of this is the practicing of the different shifts and the recognizing of the different shifts. So yeah, these aren't necessarily the same. I shouldn't give that impression. I'm just rewriting it to match the function that I happen to graph. I accidentally graphed the ln. Last but not least, minus ln of minus x. There's two shifts in this one. There are two reflections. What would they be? Good, the x and y axis. So that's flipped around the x axis, flipped around x, and that's going to be flipped around the y. My suggestion is to start with this graph. We already know what that graph looks like, and there's just one more reflection, translation, flip to do with this one, and that is flip it around the y-axis. So see if you can't figure out what that would look like. So basically you're going to take this and flip it over here. And you're going to get something to look like that. So y equals minus ln of minus x. So 4 different kind of translations of that graph. Okay, I think this is a good place to stop here. And let's see, I'll get you some homework after the break.